These are on Blackboard, by the way.
Oh, okay.
Spectrum. This is cyclohexane, the infrared spectrum of cyclohexane. And it's from the SDBS, that spectral database that's free to everybody online. Infrared is all about functional groups. Do you have an alcohol? Do you have a ketone? Do you have a carboxylic acid, etc.? It's not about mass. Remember, HNMR is all about hydrogens. CNMR is all about carbons. Mass spec is all about mass, and in particular getting the mass of the whole molecule. Infrared is about functional groups. Do you have, or don't you have, for instance, an OH group? Now, all molecules have some saturated carbon and hydrogen. That's very unusual to have a molecule that doesn't have some carbon and hydrogen of some type. Cyclohexane is a saturated cycloalkane. And it has a very simple spectrum because there's not much to it, and it's very symmetrical on top of that. Now, very important to understand what's happening in infrared. What's happening is that the bonds are vibrating in response to infrared radiation. Infrared energy causes bonds to vibrate like a spring. So the atoms are sort of like balls on the end of a spring. And you know that a spring has a characteristic frequency of vibration. It doesn't matter how far you pull it before you let it go, that's amplitude. It will still vibrate with the same frequency based on the masses at the end of the springs and what we call the force constant of the spring. Chemical bonds are like that. They vibrate at very specific frequencies within the infrared region. So every different chemical bond in your molecule has its own specific frequency of vibration. The x-axis is basically a frequency axis. You don't even need to bother with units. It has pretty weird units. It's just a set of numbers that run from 4,000 on the left down to about, well, it varies on the right, typically down to 500 or 200. This runs down to basically 500. This is 500. This is 4,000. We call them, the units, reciprocal centimeters, the centimeters to the -1. Don't worry about the units. Basically, it's high frequency on the left and low frequency on the right, or a spread of infrared frequencies. This is called the infrared region because of the way it causes molecules to vibrate. So if you stand in front of a fireplace or an electric heater, your body feels warm because the molecules in your skin are absorbing infrared radiation, which causes the bonds to vibrate more than they normally do, and that jostles the molecules, makes them move faster, and you feel the sensation of heat. But the energy is being absorbed. The baseline is up at the top. So this is sort of an upside down NMR, where the baseline is not at the bottom, but at the top. Because the Y scale is a transmittance of the infrared energy. So 100% transmittance would mean when you pass the infrared beam through the sample, at a particular frequency, it doesn't bother with it, doesn't absorb any of the energy. So you see it starts out flat there at 4,000, and then around 3,000, you get a sharp dip. That's the carbon-hydrogen bonds vibrating. Saturated CH bonds vibrate just below 3,000. Now let me give you some lines on here. You won't see this in a book, so write it down. The first line I'm going to draw is horizontally at 50% transmittance. Don't bother with anything above that line. You get a lot of little absorptions that you can ignore. You want to go for the highlights. So the highlight reel here, so to speak, is below 50%. And drops below 50%, you should pay serious attention to. Now I'm going to draw a vertical line also. At 1600. Reciprocal centimeters. So in essence, the whole spectrum now is cut up into 4 quadrants. I'm going to ignore this quadrant and this quadrant. But for all but one assignment, you're also going to ignore this quadrant. So the highlight is the lower left quadrant. Any peak that drops below 50% and is between 4,000 and 1,600, you're going to pay very serious attention to. At the risk of having too many lines here, I'm going to draw just one more, artificially at 3,000 reciprocal centimeters. That's a breaking point. You see the absorption just to the right of 3,000. That's saturated CH stretching vibration. That you will see in virtually every organic molecule. So by virtue of that, it's not terribly helpful. You can assume that you're going to see saturated CH. So if I were to look at this spectrum, the only thing I see is saturated CH. So I'm going to conclude this is some type of saturated alkane or cycloalkane. Now this doesn't seem all that helpful, but as I fill in the picture here quickly, you will see that what I'm also noticing is the absence of some very characteristic absorptions, particularly those that would indicate unsaturated CH or oxygen. Let's step through that. We'll do it quickly. Now from cyclohexane, we'll go to cyclohexene. We box off that quadrant where you're supposed to look. You see that to the right, just to the right of that imaginary 3,000 reciprocal centimeter line, you see the same saturated CH that we saw with cyclohexane. And we should, because cyclohexene still has plenty of saturated CH. But you notice that sharp line just to the left of 3,000. Those are the hydrogens on the double bond. That's unsaturated CH. That would be just to the left. It rides down that line, that 3,000 line, right on the left side of it.
Saturated
So
CH.
right side of that
Unsaturated
line is
CH.
saturated CH. Just to the left edge of that line is unsaturated CH. But again, that's not really the important issue with infrared, because anything that involves hydrogen, you can pick up in the HNMR. So this is somewhat redundant. It's really oxygen that we're after. Let's move away from the hydrocarbon. And sticking with the cyclohexane theme, here's cyclohexanol.
Tertiary haloalkane.
There's your important quadrant right there. There's the 3,000 line.
SN2.
And you recognize the saturated CH just to the right of that 3,000. This very strong, very broad absorption right here is OH. It's around 3,300 to 3,500 reciprocal centimeters. It's always almost completely filled filling the chart, and it's very broad because of hydrogen bonding. So both the broadness, well, three things, the broadness, the intensity, and the position tell me that whatever this molecule is, it has an OH. That's a big deal. There are only three types of oxygens.
OH. Two methyl, propane, two all.
There's the alcohol, OH, the ether, COC, and the carbonyl, C double bond O. This is one of the three types, and it's unmistakable. Now, very important point. If I see strong, broad, 33 to 3500, I have an OH. If I don't see strong, broad, 33 to 3500, I do not have an OH. No matter how much you want to have one, you do not have one. In fact, not seeing a peak is even stronger evidence than seeing a peak. I could just have a wet sample. Water has plenty of OH. So if your sample is dripping wet and doesn't by itself have an OH, you're going to be fooled. But if I think I have an OH and I don't see any peak there, game over. There is no OH. So it's important to note what might have been there and to say, well, okay, I don't see it, so I don't have an OH. In this case, I do.
Game over.
The other type of oxygen that's very common, the carbonyl, appears between 1800 and 1600. Sort of right smack dab in the middle of the spectrum. And of course, we don't see anything there. It's a little tiny peak, but that's not below the 50% line. So this does not contain C double bond O oxygen. It does contain OH. And the other type, the ether oxygen,
Ether oxygen.
is over in the right-hand quadrant that I said to stay out of. But this is the one time you have to go in there. Between 1300 and 1100, a very, very strong, probably the strongest band in the spectrum would be due to the ether oxygen. How strong a band is depends on the polarity of the bond. The more polar the bond is, the more intense the absorption. So all of these bonds, COH, COC, C double bond O, are very polar. That's why they're very strong. Now, emphasizing that, here is
Carbon, oxygen, carbon, potassium.
cyclohexanone with the C double bond O,
Abbreviate that.
but not the OH. So you see here, there's no OH. There's a little peak way up top there that's probably atmospheric moisture, the OH from water, but you can ignore that. I have some saturated pH just to the right of 3000, and there's my C double bond O, very glamorous, very strong band right in the middle of the spectrum. Now, in terms of the third type of oxygen, I'd be looking in this region for, if I had a COC, an ether oxygen, I would be looking for a band that is stronger than any other in the spectrum. Now, there are some peaks in there, but I'm suspicious that they're not strong enough. The ether assignment, honestly, is the hardest to make because it's in what we call the fingerprint region where most of the absorptions are. All those, you notice all the peaks to the right and the right half, almost all of the peaks in the spectrum are in the right-hand half, which I said not to look at. That's because those are very complex absorptions that don't involve the stretching of a single bond, but there's several bonds moving together. For instance, if you look at the infrared spectrum of water, you'd say, well, there's only an OH bond in water, so it should have just one absorption. Actually, it has about 16 because of the different modes of vibration. There's one where the two OH bonds vibrate in and out in synchronization like this, and a different frequency where one goes out while the other's going in like this. That's a different vibrational mode that involves both bonds together. And then there's what's called a wagging mode that goes like this, or a rocking mode that goes like this, or a scissoring mode that goes like this. It's actually quite complicated. So in a big molecule, you can have, for instance, 12 carbon-carbon bonds all vibrating as a unit at a unique frequency. Like the sound you would get if you ran your hand along a set of guitar strings. You get a unique sound that isn't just one string vibrating, but all of the strings vibrating together.
It's a
So
chord.
infrared can be very complex,
I said it's a
particularly
chord, not a note.
in the right-hand half. The left-hand half tends to be just single isolated bond vibrations, like an OH. Now, why would an OH kind of vibrate by itself? It's because it's such an unusual kind of bond. The frequency is very different from the vibration of a carbon-carbon bond. So they tend not to pick up harmonics from each other. All right, so what about an ether? There's an ether, diethyl ether. You can see there's no OH present in the infrared. There's saturated CH, no carbonyl right in the middle between 1800 and 1600. And by the way, that wide range is because you have so many variants of a carbonyl. You have ketones, aldehydes, carboxylic acids, esters, etc. They're all between 1800 and 1600. Now, right here is the ether band, COC. It's right where it's supposed to be, and it's stronger than any other band in the spectrum. So I'm going to bet that there is an ether oxygen, but I always hedge my bet with an ether oxygen. I'm suspicious, and I'll go with the oxygen initially, but if I run into a brick wall later on, as I try to put the puzzle together, I'll go back and say, well, maybe I don't have an ether oxygen. Maybe it just looks like it. So be very wary of that last type of oxygen. Okay, so that's a very quick run through, and
Let's stop
these
there.
are to be used in combination. And I think I went through this before. You can look at the infrared to see whether you have oxygen. You can look at the mass spec to see whether you have halogen, and then get a mass. And depending upon whether you have oxygen or halogen, you subtract those items from the mass to get down to pH, and then figure out how many carbons and hydrogens that would have to be to make a sensible structure, and then you've got your formula. And then you take your formula into the NMR, you know how many hydrogens you're supposed to have, so everything kind of shapes up from there, and then you do a final check if you need with the carbon NMR. So if you have a pure sample, at least this day and age, 5 milligrams of a pure organic compound, you're supposed to be able to determine the structure. It may take a while, but the tools are there. Okay.
Let's stop there.
this is important, particularly important because alcohols are such a ubiquitous class of organic compounds. Alcohols are really a favorite class of compounds with organic chemists and biological chemists because they're very stable but very malleable. In terms of their chemical properties, you can turn an alcohol group into any other kind of functional group rather easily. So if you're a card player, if you're a poker player, it's like having a wild card. If you're doing synthesis and I see an OH,
Yeah, alcohol is
great
very
if I
important when I'm
need to
playing
have an
poker.
OH there, but if I needed that OH to be some other functional group, I know that there's a way for me to do that. So OH groups are stable, they're malleable, and they're typically non-toxic, at least if you don't ingest them. Now, ethyl alcohol, of course, is famous because it's the only alcohol that your body can metabolize, even in the smallest amount. And it does have a very limited ability to metabolize ethanol. But all of the other alcohols are instantly poisonous and possibly even deadly. The alcohols,
Can't play poker without alcohol.
of course, have this generic formula, ROH, where
Wow.
R is alkyl, cyclo, alkyl, or aryl, which would mean benzene or a substituted benzene. But generally, R is used as a place marker for a relatively unimportant or less important organic part of the molecule that's mostly carbon and hydrogen. Now, that means that an alcohol has bipolar properties. The R, as you know, is nonpolar, like methane, ethane, butane, that you have their butyl group, nonpolar. The OH group, on the other hand, is the most polar neutral organic functional group. Neutral. I'm talking about like an O- or some other charged species. If you have a neutral functional group, the OH is the most polar of all of them. It's the most water-like of all of them. So the alcohols are the closest to water of any organic compounds. And indeed, the smaller ones are totally soluble in water. Methanol, ethanol, propanol, butanol. However, as the carbon group gets bigger and bigger, you can readily understand that the water solubility begins to fall off, because there's a battle going on there between the nonpolar part and the polar part. The break line is about 6 carbons. When R gets to be about 6 carbons, the alcohol starts to lose water solubility. And when you get to 8 carbons, like octanol, it's totally insoluble in water. So you know that this is methanol. That's the IUPAC name. The class ending for alcohols is OL, which makes sense. The AN is a little bit mysterious. It's just come in there because chemistry is a worldwide subject, and the pronunciation of methanol gets a little difficult if you take out the AN. Particularly, British will don't say methyl, they say methyl. So you end up saying methyl, which doesn't come out right. So historically, the AN is really in there for ease of pronunciation. Methanol or methanol, same thing. Otherwise, just ignore it. It's a 1-carbon alcohol. And methanol is completely soluble in water. Because the alcohols are so common, they have common names. Methanol is also called wood alcohol by a lot of people because, believe it or not, you can make methanol industrially by a special type of decomposition of cellulose, basically by what's called destructive distillation of wood. Produces huge amounts of methanol.
2-methyl propane 2